Got yet another determinant, another 4x4 determinant, and we're going to talk about a different strategy that can be taken to solve some of these. So determinants are pretty important, and that's why I wanted to make a lot of videos going over different methods to approach these. So in this one, we're asked to do row reductions to try to bring this to upper triangular forms. We want zeros all along the diagonal. Because the determinant of a triangular matrix is really easy to compute, but one of the things we do need to do is sort of be mindful of what happens along the way. So there's plenty of other videos going over row reduction. So I'm going to just kind of cheat a little bit and fast forward and say what the row reductions are that would take place here. So first one you might do is swapping row 1 with row 4. You know that I love to get that 1 as my pivot. So this is going to be the first row reduction. And I'm not going to show these. If you want to follow along by hand, by all means do so. What I want to do is just kind of demonstrate what they are, because they are actually important in figuring out what the final determinant is. So the next thing I might do is get rid of that 2. So row 2 is going to become row 2 that's row 4, because that's where that will be now. It's going to be row 4 minus 2 of row 1. And then I would just sort of swap through, like keep going through and doing a bunch of row reductions. If you want to pause and do them, maybe it's good practice. But we end up with just a big slew of these actions. And this will be row 4 becomes row 4 minus 2 of row 2. And we end up doing row 4 becomes 16. Row 4, and you might bring this down to triangular form using some other procedure. Not necessarily asking for row reduced echelon form, but just some echelon form. And then finally, the last action that we would do is again to row 4 minus 5 times row 3. And what you would get through steps 1 through 7 here is going to be this new matrix. So I'm not quite looking at the determinant yet. So we get this new 4x4 matrix that is basically going to be 1, 1, 2, 5. So I brought that last row up. The second one is going to be 0, 1, -3, and -9. And I will have 0, 0, 16, 46. And then finally, the last row ends up being 0, 0, 0, and 106. So take my word for it, or just do the steps yourself and verify that. But what we get is this new matrix. And so something we have to be mindful of is that the determinant of these two matrices isn't necessarily going to be the same, because basically what happened was there were 7 operations that took place here, and each of those operations may or may not affect the determinant of the outcoming matrix. And they in fact do. So just to kind of describe what these effects are going to be. So this was the original matrix, and we're trying to find this determinant value. We don't quite know what it is. This last matrix, I can actually compute the determinant of this pretty easily. I'll call this D prime. So because it's upper triangular, we just take the product of the diagonal, and hopefully you can see that by using the cofactor expansion in a particular direction. But we get this number here. I'm not even going to do that calculation. I'm just going to say it's 16 times 106. You can run it in a calculator, but I don't happen to have one handy right now. So they're not necessarily equal. In fact, they're not going to be equal here. So if we actually trace through the effects of these changes, so swapping 2 rows is going to multiply by -1. So it's going to multiply my D, my original matrix, by -1, the determinant of it. So this adding or subtracting multiples of one row to another, which is essentially what the second action is, doesn't actually affect the determinant at all. So it doesn't have any outcome. Swapping again, so we're going to multiply by -1 again. Again, this is subtracting a row from another row, subtracting a row from another row. Now, multiplying a row does have an effect, and that is going to be to multiply by that multiplier. So we do need to be mindful of this. And then finally, subtracting a row or multiples of a row from another row doesn't have any effect. So what we've got here, if we set this up, is a bunch of things happening to this value D, this determinant, that gives us the resulting determinant. So in order, if we kind of wanted to go with like how these things affect the matrix, the first thing is this -1, so I'm going to write it right beside it. And then the next one, now this order doesn't matter because it's just scalars, it's real numbers, but it's kind of consistent with how we would do matrix multiplication. So I'm just doing the order, in the order in which they affect D. And then this gives me my new resulting output, which was actually 16 times 106, whatever that happens to be. The reason why I kept the 16 is I did know going in that we can just cancel the 16s, and the result is that D is 106. So just a really common mistake that I do see with a lot of these problems is that people will keep track of the changes that occurred and realize, for example, we multiplied by 16, but then what they'll do is multiply the determinant of the new matrix by 16 to get the determinant of the old matrix. When it doesn't work that way, that multiplier of 16 happened to get to the new matrix. So we have to undo that action. And so that's why it would end up actually getting divided out. This is our determinant, and of course it's not invertible. That's right, it is invertible. I don't know why I said it's not invertible. It is invertible, it's not 0. My apologies.